Thank you, Alexis. I'm Beth O'Donnell. I'm with the Virginia LTAP, and it is my pleasure to introduce our speaker today, Trig Hoff. Trig is the Northeast Region Engineer for the American Concrete Pipe Association, otherwise known as ACPA. And Trig graduated with a BS in Civil Engineering from the Ohio State University. And his professional experience ranges from environmental consulting in Ohio to architectural engineering in beautiful Lake Tahoe, California. Trig has been promoting resilient infrastructure with the ACPA since 2012. So we're very lucky to have him. And Trig, I'm going to pass it over to you so you can get started.
Great. Thanks, Beth. So we are going to cover Engineering 101, some basic concepts for non-engineers. And certainly if you have any questions, like Alexis said, please feel free to enter those in the chat box, and we'll either stop and address those, or we'll hit them all at the end. But I want to thank everyone for joining us today, and let's kick this off. So right off the start, we're going to start with the poll, and we're going to have a few of these sprinkled throughout the presentation just to get some interaction going. So Alexis, if you could launch the first poll, please. So which of the following best describes your current position? I would assume some of you are inspectors. We might have some constructors, and by that I mean if you work for an agency and you're out in the field building anything, really, pipe, roadways, buildings. Be interested to see if we have any contractors on the line. It looks like we have some engineers on the line, which is also interesting. So you guys, please feel free. If you think I'm saying something you don't agree with, let us know in the chat box. I'd love to make this a discussion rather than me preaching to you about my take on engineering. And then we have quite a few folks, it looks like, are in the other category. So if you guys want to input what your positions are, if they don't fall under one of these, into the chat box, maybe we could discuss that at the end too. All right, it's starting to slow down. We're at about 80%. If we could get a few more folks in the next 10 seconds or so. All right, I think I'm going to go ahead and close this poll down. And I think everyone can see the results there. So we have about 19% of you are inspectors, 10% are out there in the field building things. No contractors on the line, or you're just telling me that to see if I'm going to badmouth contractors as an engineer. And I promise you I'm not going to do that. 22% of you are engineers, and 49%, so almost half of you are not any of those. So that's interesting. So we will hopefully, for the half of you that don't associate with any of those positions, like I said, please let us know what your role is. It's kind of fun to see, and then we'll kick this off.
Trig, the chat box has a lot of interesting answers to that question.
Oh, great. Okay. Let's just to make sure that we get through everything, let's read off some of those when we get to the end, because I think it's kind of fun to see what everybody does. All right. So my computer will participate. There we go. All right. So these are the basic concepts we're going to be dealing with today. We're going to do a very brief, and I mean brief, introduction to engineering, just kind of looking at some of the different disciplines that are out there primarily. And then we'll take a closer look at structures. And when I say basic concepts, I mean very basic concepts. We're just going to look at almost just building blocks that engineers typically use from a structural standpoint. And then, as Beth mentioned, I'm with the American Concrete Pipe Association. And so for us, from a pipe industry standpoint, certainly we're interested in pipe, but we're also interested in the backfill and the soils that embed the pipe and then allows the soils and the pipe to work together as a system. So we'll spend a little bit of time on soils and a little bit of time on water, obviously from a pipe standpoint, and then we'll wrap it up. So let's talk about some of the intro. The intro to engineering. So there are a lot of different types of engineers. Certainly, most people have heard of civil engineers, mechanical engineers, maybe electrical, maybe chemical, but there's a lot more than that. And here's just this is actually probably a brief list of the different types of engineers. This list is just from the Ohio State curriculum, the Ohio State University curriculum. And as I mentioned, I'm a civil engineer. But actually, my first 2 years at Ohio State, I was a welding engineer, and then I switched disciplines. So there's a lot of different disciplines out there. Those of us that are in the transportation industry probably interact with a lot of these. So for example, civils, you're going to run into those. Civil engineers often are dealing with transportation projects, drainage projects, environmental projects like that. You may bump into a materials engineer as you're working with asphalt or concrete. You'll probably at least touch base with some environmental folks, mechanical, possibly electrical, possibly petroleum or chemical engineers if you are dealing with the asphalt section of the transportation industry. And each of these, even though that's a lot of categories, each of these can then be broken down into even more subcategories. So at Ohio State, when I was studying civil engineering, I could have focused on construction services or geotechnical, structural, land development, transportation, hydraulic, environmental, and in fact, architectural, I don't have listed there, but that's a subcategory as well. So one thing you'll notice is that some of these are primary categories and they're also subcategories. So it gets a little confusing. And certainly as a civil, I'm confused about what anyone in nuclear is doing or ocean engineering. So we really, as engineers, we try to focus, we don't try to, we do focus our practice as well as our studies on one topic. We really want to be we want to be specialists in that one thing rather than a jack of all trades. Doesn't really cut it. Now, if you're not in the industry or if you're not in the civil engineering community, a lot of these words are almost like a different language. It is really like Greek, and just to illustrate that, I've added some of the Greek letters that we use a lot. So
Beth, am I muted or is he frozen? Am I frozen or is he frozen?
I think Trig is frozen.
Okay, alrighty.
Can others give a reaction, a thumbs up, so we can see that you're all live? Yep. Okay, there's some confirmation.
Okay, all right. Then would Beth,
I will contact him and ask him to leave and click on the link again.
Okay, that sounds great. All right, you guys, let's give him about 1 minute to get back on. If not, I'd be happy to share my screen and I can pick up where he left off.
And Alexis, you could look at the chat box and actually invite people to share. There were some really interesting roles that were shared in the chat box. Okay. Might be a good discussion.
Yep. All right. Go up to the top. Okay, so it looks like we have Public Works Director, Township Manager, GIS Manager, Superintendent. Oh, Mayor, that's pretty neat. Ida, can you comment more on that? Program Manager, Survey, Director of Finance, Accounting Manager, Retired Engineer, and Geologist. So a retired engineer, can you comment more on what you did before you retired?
You'll have to click unmute so that we can hear you. And Alexis, I have not heard back from Trig yet.
Okay.
So that may mean that he's lost total connectivity.
Okay.
Do you have speaker notes by any chance?
I'm pulling, there are no speaker notes.
Okay.
Okay, I'm the mayor of a small borough in central Pennsylvania, about 12 miles from State College. We are Penn State. I got a couple Penn State comments in there. Environmental, also worked in Afghanistan. Wow. Oh, got some Ohio. I see some rivalries going on now. That's great, everyone. Okay, can I ask? Yep, go ahead, Beth.
I was just going to say, I'm pretty confident Trig is probably scrambling on his end to join us again. And so he'll find a way to reach us. In the meantime, I think I would encourage people to unmute and actually have a conversation because, there are a lot of us here, 80 people have decided to participate in this. And I'm really curious as to what drew them. I know what drew me here. This topic is something that I was very excited, might have been the one that I personally was most excited about because of its relevance. We all of us on our staff at the Center for Transportation Studies, we work with engineers every day. And yet our staff does not, actually recently we hired an engineer, but otherwise, the terminology and the concepts, they surround us. And so to actually be handed some language to use to connect with that. But I'd love to hear other people's reasons why they were drawn to this topic. So I encourage anyone who wants to unmute and share that.
Beth, I know I was personally excited because in what I do, I actually work with anyone ranging from like your boots on the ground to engineers. So it's really neat to just learn the concepts and have some of that background knowledge. And it helps me feel more confident participating in discussions and conversations with them.
Mm-hmm.
Yeah, hi, Beth. I was also excited about this session. I remember years ago, I had friends that were mechanical engineers, and I was like, what is that? What do you do? And they seem to do a lot of stuff with computers, at least the mechanical engineers that I knew. And just within the civil and environmental world, I think of the difference between traffic engineers and transportation engineers. So I think just, having a greater understanding about this is really useful.
Thank you, Kim. Yes, and I see several of my staff members, I should say the Center for Transportation Studies staff members. I would love to hear from you guys. And I'm going to go unmute and I'm going to call Trig right now.
That sounds great.
Yeah, I'll just ditto what everybody's been saying. I'm a county manager, so but I'm surrounded by engineers. My husband's an engineer, and so I'm very interested in this topic too.
Thank you, Becky. Okay. All right. So what I think I'm going to do is, Beth, I was actually able to recover a PowerPoint that does have speaker notes. So I'm going to share my screen so that we can look over those. Can you guys see that? I know it's not on slideshow view quite yet. All right, great. Give me one moment to get there. All right, I believe we left off on, he was talking about the Greek letters, is that correct? So we're on structures.
Mhm.
Okay. All right. Let's start with a look at the structural side. So the most basic form of the structural design takes into account the behavior of rigid bodies. I say rigid bodies because as engineers and contractors, we typically deal with rigid bodies rather than flimsy or floppy bodies. If we can't estimate how a still body or a body in motion will move, then we can struggle to design a safe structure. Indeed, the less rigid a body is, the more difficult a design becomes. When engineers begin their college coursework, ooh, Trig, I see is entering the room. One of the first classes is a study of statics. Let's see, Beth, do we have Trig back in?
Hey, I'm back.
Hey there.
Well, sorry, Trig. Alexis already gave your whole presentation. So we all are now ready to go be engineers. But thank you for trying.
I'm really sorry about that. I haven't lost my internet connection in a year, and it suddenly decided to go out just now.
Well, we are thrilled that you're back. So we'll let you pick up right where you left off.
Okay, where did I? Honestly, I was still going. I didn't know I lost you guys. I gave a brilliant presentation. The last 10 slides.
I think if you pull up the structures theme slide and go from there, that would be great.
Okay, so behavior of rigid bodies.
Yes.
And Alexis, it's not letting me share. If you could open it up.
Okay, give it a try one more time.
All right. How's that look?
Looks great.
Okay.
All right. Did we lose Trig again?
Okay.
Oh.
I'll repeat it for those of you that were logged off as my internet went down. So are you still, is it still coming through, Alexis?
Yep, you're good to go. I turned off your video just to help with bandwidth.
Excellent. Okay, thank you.
You're welcome.
Okay, so let's talk about the behavior of rigid bodies. When we're looking at structures, we are primarily looking at rigid structures. So we're not, from a transportation standpoint, we're not looking at flexible, floppy type structures. The stiffer the structure, the better we're going to be able to estimate how it's going to behave due to certain loading. When we're looking at the behavior of those rigid bodies, we look at it from three primary, very basic standpoints. From statics, meaning we're studying that structure when it's not moving. Dynamics, we study that structure when it is moving. And then the mechanics of materials, we want to be looking at the at how that body reacts to those loads. So let's take a quick look at each of these. And looks like PowerPoint thinks that I am in the wrong spot. There we go. Okay, so let's take a look at each of these. So first, statics. Statics is the study of the loads and the forces that exist when an object is loaded and it's at equilibrium. So what we mean by equilibrium, it's not moving, okay? So if we take a ramp and we place a block of wood on that ramp, we all know that it's going to experience gravity. That's one of the basics that we all are aware of. So the force of gravity is pulling it straight down, trying to pull that block of wood to the center of the earth. Now, Isaac Newton tells us that there need to be equal and opposite reactions. So in other words, if the force of gravity is the only thing that's acting on that block of wood, the block of wood is going to try to fall through the ramp. Obviously, something is keeping that from happening. And what's keeping that from happening are two different forces. One is the force of friction. The force of friction keeps that block of wood from sliding down, because remember, statics, we're looking at it not moving. And the normal force. And normal is just another way of saying the perpendicular force. So that force is what the block of wood is doing, what the ramp is doing to our block of wood. Now, F sub n stands for the normal force, And that's a reaction force, meaning it's reacting to the gravity. And that reaction force is just another way of saying thrust. So a lot of times you'll hear the term thrust thrown around. Thrust is the reaction to a different force. Okay, now let's look at, excuse me, let's look at dynamics. Dynamics is when we add just enough load that that body starts to move. So we take our same block of wood on that same ramp. It's still experiencing gravity. It's still experiencing the pushback from the ramp, and it's still experiencing the force of friction that's keeping it from sliding. But now we add a new force. So let's say we just tap it with our finger and that block of wood starts to slide. So in this case, the force from our push was just enough more than the force of friction to get the body to move. So that's a study of the dynamics of that block. Now, what would happen if that force of friction was really strong? Let's say it's on sandpaper on the ramp, and we apply enough force it to move. What's it going to want to do? Well, it may want to slide. There's a possibility, even with that 60 grit or 40 grit sandpaper, it might still slide along that ramp, but it may not. It may grip it so much that when we apply that force, the block starts to rotate and then it rolls off the ramp. So that's another aspect of dynamics that that we can study when we're looking at all of these different rigid bodies. So now let's jump to the next category, mechanics of materials. Mechanics of materials is a study of what happens, what does that block of wood do when we apply the load and it doesn't necessarily move? Well, the strength of the material might impact what happens to the block. So maybe the block collapses if we have too much of a load on it. So Alexis, I'm actually going to skip the second poll just for the sake of time.
Okay, sounds good.
So we'll keep running. But it's good that we had that poll in there because I got here and I realized that no one else was here with me the first round. So I'm glad we had that in there. So that's the behavior of rigid bodies. We're looking at the statics, we're looking at dynamics, and we're looking at mechanics of the material or the strength of material. Now, how do we analyze that behavior of rigid bodies? So one of the givens is that all objects are going to deform under load. Now, when I press down on my desk, it doesn't visibly deform. But microscopically, if we're dialed in super close, there is a little bit of deformation there. And so we could measure that, certainly. And the mechanics of materials tells us how to determine how much it's going to deform. So the material of this wooden desk is pretty strong. And so you're not going to really see it deflect much. But if I were to push on some Jell-O, you would see it deflect quite a bit. So the difference in the strength of that material and the stiffness of that material all plays into how those objects deform under load. So there are two key concepts here when we're looking at how rigid bodies behave. And those two concepts are stress and strain. And you guys have all heard of stress and strain, both personally, certainly in the last 6 months, but also you've heard about it from a structural standpoint. I'm going to go out on a limb here and say that you have. So let's take a closer look at both of these. So stress is the measure of the intensity of an internal load acting on the object. And sometimes it's difficult to remember which one of these is which. Remember, stress is what you feel day to day when you're at work and you are stressed. And it's just tearing you up inside. You're not showing any physical reaction to that stress outwardly. It's all internal. With strain, it's the other opposite end of the spectrum. With strain, you're actually deforming. So when your arm breaks, you didn't stress your arm, you strained your arm. Now, certainly stress and strain work together, and we'll talk about how they work together. But the very basic concepts of stress and strain, stress is internal. We can't measure it, but we can calculate it. Strain is external deformation, so we actually see that change. So let's look at some different stresses. We're going to look at three basic categories of stresses: axial stress, bending stress, and shear stress. So let's look at axial stress real quick. Axial stress means the forces that arise from internal loads that act along the longitudinal axis of a member. So we're showing two different types of axial stress in this slide. One is tensile stress, so in tension. That rope that we're showing at the top is in tension, so that's pulling it along the longitudinal axis, so it's lengthwise. And the other bit is compressive stress, and we're showing that with the elephant sitting on the column at the bottom of the slide. Now, we calculate axial stress by taking the load that's being applied, so in this case, an elephant. So how much does the elephant weigh, and what's the cross-sectional area of that column? So if we were to slice that column horizontally, we could measure what its cross-sectional area is, and then we would take the weight of the elephant divided by that cross-sectional area, and that gives us the axial stress in that column. Here's the equation for that. Let's take an example, just a really easy example. This is going to be some very simple math. If we had a 1 inch by 1 inch concrete bar, let's say, it doesn't really matter how long it is, but if it's 1 inch tall, 1 inch wide, and let's say 10 feet long, the cross-sectional area, if we slice that bar down the middle, is going to be 1 inch times 1 inch, which is 1 inch, 1 square inch. So the area of this bar is 1 square inch. If this bar was 10 inches long or 100 inches long, that doesn't matter. We're just looking at the axial stress on this bar, which is the cross-sectional area. It doesn't take into account the length. So if we took that concrete bar, we put it in a vise and we spin the dial, and we apply a 10-pound load, how much axial shear is, I'm sorry, I shouldn't say shear, how much axial stress is the bar experiencing? So the load is 10 pounds. We know that cross-sectional area we just calculated is 1 square inch. So it's 10 pounds per square inch. So that's our PSI, pounds per square inch. Okay, so you can denote that PSI, you can denote it pounds per square inch. Both of those are kind of interchangeable terms. Okay, so we mentioned the differences between tension and compression. Tension is where that rope is holding a load. Compression is where we have a column that's supporting a load. Now let's look at bending stress. Bending stress is an interesting one that's a little bit different. So bending, also known as flexure stresses, they develop in an object when there's internal bending moments, and they're caused by a perpendicular load to a longitudinal axis. So looking at those palm trees, let's assume that they're bent over because of a windstorm, rather than that's just the way they're growing. Okay, so let's look at what the bending moments, those internal bending moments, are. So a bending moment is the measure of perpendicular force causing a body to rotate about a point or an axis. So in this case, with our palm tree, we're applying a wind load at the top of the tree. What are the two forces acting on this tree? Well, we already talked about it with the block of wood earlier. Obviously, we've got the wind load, but obviously we also have the force of gravity pulling that tree down. And it's trying to pull that tree right through the ground, but Isaac Newton tells us, no, something has to keep that tree in place where we can see it, so it's in place. So that is the resultant force pushing back up from the beach. But we don't want that tree's not sliding across the screen, is it? So something must be holding it in place, so there's a resultant force that's pushing back the opposite direction. Now, if you look at that force of the wind, pressure of the wind, PW, and the resultant of the wind down at the root ball, they're pushing in opposite directions. If you think about it, that tree is really wanting to twist because it's got somebody pushing it to the right at the top and somebody else is pushing it to the left at the bottom. It wants to twist. Something keeps it from twisting, and that is the moment that is created by the root ball of this specific tree. So the moment of the ground, M sub G, is what we would call that. And moment is a measurement of force times distance. So in this case, there's a moment at the base of that tree that's resisting the wind pressure. So that's our force, PW, times the height of the tree is our distance. So let's call that L. we do what we call a sum of moments. So again, Isaac tells us everything has to be equal and opposite. So the sum of all these different forces has to equal 0. And we can calculate that moment in the root ball by summing everything to 0 and then doing the calculation. We're not going to get into those calculations right now, but that gives you an idea of what these bending moments are. So let's do a look at the bending involved in a concrete beam. Okay, so we have the equation for bending is the moment at the bending axis, and we'll talk about the bending axis in a second. That's multiplied times the perpendicular distance. So remember, the perpendicular distance on that pine tree was the height of the pine tree. And then we divide by the moment of inertia. Okay, so this is our bending axis. We apply a load from above. That beam is trying to bend around that dotted line. Okay, let's talk about the moment of inertia that's in the bottom of the equation. The moment of inertia is just a measurement of how well a body resists bending and deflection. So take, for example, we talked about if you were to break your arm, the strain that it experiences. If you're applying a load to your upper arm and it wants to break, the resistance to bending that the bones are creating is the moment of inertia of your arm. Now, if we're just looking at a rectangular beam, that's a pretty straightforward calculation. It's 1/12 times the width of the beam times the height of the beam cubed, okay? So if you're looking at this equation, you'll notice that there's one b in the equation, but there are 3 h's. That's what we mean by cubed. So there are h times h times h. So if that load is being applied from above, that beam, the height of the beam is way more important than the width of the beam, because I stands for the resistance to bending. So the more H's we have, so if it's a tall beam, the more H's we have, the more it can resist the bending. So if you were to flip that beam on its side, it would not be as strong because now its height is much shorter. So think about your floor joists in your house. You'll notice, if you've ever watched construction of your house, floor joists are oriented this way with a lot of height, not very much width, okay? Now, if we were to get into a more complicated shape, like a triangle, you can see that the moment of inertia gets crazy. So I'm not even gonna get into that, but those are the calculations for the bending of a triangle. And then, as I mentioned, I'm in the pipe industry. So when you're looking at a corrugated pipe, corrugated plastic pipe actually gets its strength from the corrugations. So those corrugations are trying to resist bending. And to calculate that, you have to know what the moment of inertia of that corrugation is. So if you look really closely at one of those corrugations, and let's see if I can highlight it here with my mouse. If you look at this corrugation, calculating that is going to be really complicated if you think about how difficult it was just to do a triangle. So there's a lot of math that goes into this. Typically, your pipe producer is going to give you that information rather than requiring an engineer to calculate it. Now, bending also has tension and compression, just like the axial loading did. So if we take this beam and we apply a load from above, and the beam starts to bend, part of the beam is going to go into compression and part of the beam is going to go into tension. And you can see on our little blocks to the right that the blocks on the top are getting squished together and the blocks on the bottom are getting pulled apart. And that's compression forces and tension forces. So compression, we're trying to squeeze those particles together. Tension, we're trying to pull or stretch them apart. So take it back to that concrete beam concept. If we have a concrete beam, we apply a load right in the middle, just like we did with that foam beam on the previous slide. Where would you expect the compression and the tension zones to be? So you push down on that beam and you can picture it in your head. That beam wants to bend down in the middle, and that means the particles at the bottom of the beam are trying to stretch out. Particles at the top up near the load are trying to push together. So our compression zone is at the top where they're pushing together. Our tension zone goes to the bottom where they're trying to pull apart. Where would we want to put reinforcing steel? Well, one thing that we haven't talked about yet is on the strength of materials For concrete, concrete's really strong in compression. It's not nearly as strong in tension. So we help it out. We add reinforcing steel to the tension zone, which is red in this example. And that's where our reinforcing steel should go. Okay, so if we were to look at that beam with a finite element analysis, and basically that's just a fancy way of saying we're going to model it with a computer. You would see your compression zone is in blue in this beam. Your tension zone is in red. And you can see a couple sticks of reinforcing steel inside that beam. As that load is applied, the concrete is going to experience some stress and then some strain. So the dotted line is the stress in that concrete pipe, and then it drops off. You can see when it gets to, 2 seconds, all right? Now let's look at what happens to that reinforcing steel. At the exact same spot, at 2 seconds, that reinforcing steel it's just kind of going up, and then suddenly it's like, boom, I'm engaged. And what's happening here is the concrete is cracking, and so if there's a crack, it means the concrete's moving. Therefore, the steel has to be picking up load. That's why we see that steel jump up on the chart there. So the crack is simply a stress transfer. So it's transferring the stress to the steel, and then the steel engages and carries the load. So that was a little deeper probably than we needed to get on the discussion on bending, but I do like to point that out. So let's talk about shear very briefly. Now, we're all familiar with the concept of shear, but we maybe don't realize it. Shear is really the concept of scissors. So even in grade school, we all understood that we could take a set of scissors and squeeze the handle on and put the blades at a piece of paper, and it would cut that piece of paper. And that is technically shearing the piece of paper. That's known as direct shear, where we have a load almost directly opposite on either side. Flexural shear is when we have that load applied over a larger distance. Okay, so let's look at each of those. So with direct shear, let's put our concrete beam here in this, and we'll apply direct shear, just like scissors, on this concrete beam. So I've spread the point loads out a little bit, but just imagine they're right next to each other in terms of the closeness. Now, as they're pressing up and pressing down, if we took an imaginary cube out of that concrete beam, we could call that unit shear stress. And if you notice how we have the blue arrow pointing up, red arrow pointing down, that cube, that unit shear is trying to rotate. But remember, Newton told us there has to be equal and opposite reactions. So the only thing that's keeping that little piece of concrete from rotating are forces pushing in equal and opposite directions from those two loads that we're applying to the beam. Now, what does that look like? It kind of looks, to me anyway, like a couple of dogs pulling on the same toy, a little tug of war going on there, because you've got two arrows pulling to the top left, you've got two arrows pulling to the bottom right. What's going to happen if that was a piece of paper and we did that? It's going to rip diagonally. It's going to pull directly down the middle between where those two forces are pulling. Okay, so that is an example of direct shear. Flexural shear is if we apply those loads much farther apart. So remember, the first time we had those loads right next to each other like scissors. Now it's more like we're looking at a bridge beam or a floor joist. So we have supports at both ends of our joist. We're applying a load right in the middle. That floor joist wants to rotate, like we talked about with the palm tree. And to resist that, it has moments throughout. There's a tension zone, like we mentioned with the concrete beam. It's trying to be pulled apart at the bottom. It's trying to be pushed together at the top. That's our compression zone. And the tension zone of all materials are going to start to crack as they exceed their tensile strength. So we're showing our cracks here on the joist. And the shear zone happens at the ends. So that's where our supports are. So just like with our scissors, we had the support and the little unit shear. Same thing is true on this bigger beam that's spread out. We have shear zones at both ends of the joist. So for example, if you were drilling a hole into a beam or into a floor joist, you wanted to run your plumbing or your electric through that floor joist, you've got to be careful where you drill it, because you don't want to put it in the tension zone. You don't want to put it through the shear zone. So there are some limitations as to where you're allowed to put holes in your floor joist. And that's because of the way the behavior of this rigid body works. If you wanted to calculate your shear stress, it is the pressure. So the pressure that's being applied by that big red arrow at the top divided by 2, because we've got 2 supports here. So it's P over 2. Okay, let's look at strain really quickly. So again, strain is the deformation, meaning if that block of concrete falls on your head, you're gonna have some deformation in your skull. Different from stress, which is internal, strain is external. So if we look at strain analysis is really helpful to us from an experimental standpoint, because we can measure that deformation. And then strain analysis is also interesting from how bodies can be strained without applying any load. We'll talk about that in a second. But first, let's get to the experimental analysis. So as we apply that load, we can apply little strain gauges to that beam, apply our load. Either we pull it apart or we apply a load from above and try to bend it. Those strain gauges will measure how much the object bends, how much it moves, how much it stretches, and they can tell us an experimental value, which is pretty nice. With strain, it doesn't really have a unit. So for example, if we take that same block that we were applying compressive stress to, if that block were to deform, so with concrete, it's more likely to crack, but let's say it's steel and it just bends or it doesn't bend, I'm sorry, it compresses rather than cracking. If that block is 4 inches long and we were to get it to squeeze down 1/10 of an inch shorter than that, then that would tell us how much strain it has. It would be the change in length divided by length. You'll notice our units are the same top and bottom, they just cancel out. So strain actually does not have a unit. We usually say inches per inch, feet per feet, foot per foot, meter per meter, just so that we're aware of what units we're dealing with. But in general, it does not have a unit. So in this calculation, 1/10 of an inch divided by 4 inches equals 0.025 inches per inch. That's the strain this little steel bar experiences when we shrink it by 1/10 of an inch. Now let's talk about unloading, and Alexis, unloaded strain. Alexis, if you wouldn't mind launching the last poll here. So how might a heavy steel rail experience strain if we're talking change in dimension without any external loading? Is it from gravity? Is it from acid? Is it temperature? Are you maybe not sure, but you're pretty sure they did it on Star Trek? Okay, so we have some Star Trek fans. That's good. Temperature seems to be leading the pack right now, although gravity's a close second, and then acid is right after that. All right, so we're just above 50%. If we get some more folks giving their opinion on this, we'll give it another 15 seconds. All right, looks like we're slowing down. Let's go ahead and show the results of that poll.
Okay, everyone should be able to see those results.
Great. All right, so 70% of you said by temperature, which is interesting. It means that you've already looked at my slides. 20% say gravity, 9% aren't sure, but they think they saw it on Star Trek, and 2% said acid. So the correct answer is temperature, and we will talk about that for a second. Gravity, remember, gravity is a force. So gravity is working on that heavy steel rail at all times. It's working on all of us at all times. So that would be considered external loading. It's gravity is not inside our bodies, it's inside the earth. It's pulling us towards the center of the earth. That is an external force. So that one's knocked out. Acid, acid's not really a force. Acid is a chemical reaction rather than an external physical force being applied. Temperature we'll get to, and then Star Trek. I don't even know if they talk about this in Star Trek. I just thought it sounded like they would. So let's jump into that. And Alexis, we're going to be providing the slides to everyone. Is that right?
Yep, that's correct. They have access to them in Talent LMS.
Okay, perfect. So you guys are all going to have access to all the slides. We're not going to make it all the way through because of the internet connection issues. But we'll keep going until we run up against our time limit here. So let's talk about unloaded deformation. So how is that possible? Well, let's look at the railroad, because railroads give us a prime example of thermal strain. So this is an expansion joint in the railroad. So in the rails, every so often they'll have a gap in that rail, and the reason is because over increased temperature, that steel is going to try to expand, or it's going to try to shrink as it gets colder. And so we need these expansion joints that allow it to get longer or shorter without derailing the train. Now, sometimes if we get too much of that, we will actually get that expansion joint is going to close down, and the steel has nowhere else to go, and it still wants to expand, and then it starts to kink. And you'll notice in the photograph on the bottom, there's some extreme kinking going on. So if you look closely, there's in that photograph, there's at least 10 what the industry calls sun kinks in that railroad. And that's actually a photograph from New Jersey. This was in 2006 or 2007. In the summertime, they had a week of extended temperatures. The steel had nowhere to go. It just kept wanting to expand. And eventually it just started to kink because it had nowhere else it could go. So the US Department of Transportation has a manual on how to design for this, as certainly as we start to see more climate change and temperatures are increasing, we need to be aware of that from a design standpoint. So one of the interesting things about thermal strain is it happens simultaneously in all directions. So those rails aren't just extending in length, they're getting fatter, they're getting taller. It's just they're really long rails. So when they increase a percentage in length, you really see that more so than you see the other two directions. The amount of strain is the same in all directions. And the more you heat or cool the object, the larger the magnitude of strain. This is the equation for thermal strain. So alpha is the Greek letter we're showing there. It looks like an A. That's the coefficient of thermal expansion. And we're multiplying that times the change in temperature. And I'll give you an example from the pipe industry. The coefficient of thermal expansion for steel and concrete are both in the 6 range. So 6 times 10 to the negative 6 per degree of Fahrenheit. And that sounds crazy. So let's just focus on the fact that it's 6. And then plastic, HDPE, is around 67. So it's about 10 times as much. If what that tells us is if we were to have a 100-degree swing, so let's say you had reinforced concrete that was 100 degrees cooler, it would shrink by about 1/10 of an inch over 20 feet. If you had a piece of black plastic that cooled 100 degrees, it would shrink 1.5 inches over 20 feet. So again, from the strength of materials concept and the design of different products concept or different materials, we need to take that all into account as we're from a design standpoint. Here's an example where a piece of black plastic pipe is going into a manhole, and you can see about 1/2 inch gap there due to the change in temperature.
Greg,
that's
we are at time.
Yep.
Just
So
let
I would,
you know.
I think that's a good stopping point. We made it halfway.
Wonderful. Trig, thank you so much for your time today.